So first, I'd like to thank the organizers for inviting me to speak. It's a great pleasure. And also, I want to thank the audience to stay here after many talks. So my talk is basically on expository, about a moduli space of Calabi-Yau manifolds from the viewpoint of mirror symmetry. So when I submitted this title, I wasn't sure what to talk about to the audience with a different background. But so the title is quite flexible, but it turned out it's not that misleading. So let me begin with an introduction. As Professor Tian already talked about, a Calabi-Yau manifold is a compact scalar manifold such that the canonical boundary is trivial. Equivalently, this is a Ricci flat scalar manifold by the famous Yau's theorem. And in dimension 1, it's just an elliptic curve. And in dimension 2, it's K3 surfaces and abelian surfaces. And in higher dimension, there are many topological types. So it's basically a generalization of an elliptic curve. And I want to fix some notation. So by the Calabi-Yau condition, it carries a holomorphic volume form, which is on section, a global section of the top on wedge of the cotangent bundle. It's on nowhere vanishing holomorphic volume form. And also it's a scalar manifold. It carries on a scalar class, which belongs to H on 1, 1, X. It's a real part. But often we consider complexification of the scalar class as well. So it's called a complexified scalar form. That is an element of H11, such a way that the imaginary part is on scalar form. The real part can be anything. So Calabi-Yau manifold is, by definition, it's a scalar manifold. So recall that a scalar manifold has 3 structures in a compatible way. It's a complex manifold, of course, and a Riemannian manifold, and a symplectic manifold in a compatible way. And 2 of them determine the last one. So basically, there are 2 structures, 2 moduli spaces. And in this talk, I wanted to focus on 2 moduli spaces. One is moduli space of complex structure. The other is moduli space of scalar structure. This is a little bit on abuse of language because in fact, I talked about on moduli of a symplectic structure. But in our field, we call it a moduli of scalar structure. So when I say moduli of scalar structure, I fix a complex structure and vary the symplectic structure. Okay. So there are 2 moduli spaces. And in the last 3 decades, I think the main motivation to study Calabi-Yau manifolds come from mirror symmetry, which is a conjecture inspired by string theory. So the conjecture roughly claims that given any Calabi-Yau manifold, there exists another Calabi-Yau manifold, say X and Y, the Y is called a mirror manifold of X, such that on symplectic geometry of the initial Calabi-Yau manifold X is equivalent to the complex geometry of another Calabi-Yau Y, mirror partner, and vice versa. And of course, you have to make sense of this equivalence. And there are many formulations. And for example, Konchevich's on homological mirror symmetry on Strominger, Yau, Zaslow's dual integrable system on formulation, and many others depending on the situation. And one concrete example first studied by physicists is on quintic threefold. So it claims that, roughly claims that the quantum cohomology of a quintic hypersurface in CP4 is equivalent or contains almost the same information as Hodge theory or period integral of a mirror manifold Y. And if you haven't seen mirror symmetry before, this is just on a distribution of Calabi-Yau threefolds in toric manifolds and some plus alpha. And you see the striking symmetry along the vertical axis. And I want to explain what the vertical axis and horizontal axis represent, but this indicates that the dimension of complex moduli space of X is the same as the dimension of the scalar moduli space of Y for a mirror pair of Calabi-Yau manifold. But this is actually a trivial consequence of this equivalence, because if you have 2 equivalent geometry, then the moduli space of these geometries should be the same. in particular, the dimension of the moduli should be the same. So this is just an easy consequence, just the equality of numbers. But in this talk, I wanted to look at a refined structure of the moduli space, not only numbers, not only dimension, but the structure. Okay, so on today's talk, I wanted to see two moduli, or compare the moduli space of complex structure and Kähler structure. Okay, and in light of the mirror duality of Calabi-Yau manifolds, in light of the mirror duality of Calabi-Yau manifold, we expect that there should be sort of parallel theory between these two moduli spaces. And especially the complex moduli space have been studied quite well, and we know that it has a rich structure, and we expect the latter space is also rich. And probably another motivation to study the moduli of Calabi-Yau is that it's a basic principle that sort of a moduli space is nice if the object, its parameters is nice. So the moduli sort of inherits the structure of the object. And I think this is true in daily life too. So you should behave well in front of your kids. Okay, so I want to begin with some review of complex structure of the moduli space. So the moduli space of complex structure has a long history of study, initiated by Riemann, who first studied the moduli of Riemann surfaces, one-dimensional complex manifold, and later on Kodaira and Spencer, who studied the first deformation of complex manifold in a high dimension. And then Kuranishi, who studied who sort of showed the existence of the versal deformation space of complex manifold. And so the prototype of the moduli or complex moduli space of complex manifold is Riemann surfaces. The genus G Riemann surfaces has a moduli of, the moduli of the genus G Riemann surfaces is complex manifold of dimension 3G minus 3, and it is naturally equipped with a nice metric called Weil-Petersson metric. So it's very nice, as nice as possible. And Calabi-Yau manifold has similar properties. So, Calabi-Yau manifolds are particularly nice because of this theorem by Bogomolov and Todorov, claiming that assuming this vanishing of cohomology, this basically means there is no continuous automorphism. Then the complex moduli of the Calabi-Yau manifold is a smooth complex manifold or orbifold of dimension H1 of the tangent bundle. More precisely, the deformation is unobstructed. So the space is nice because of this theorem. And if you have a nice space, probably in modern mathematics, if you want to study space, you often consider nice functions on it, like mode theory. And what functions are there? For Calabi-Yau manifold, say n-dimensional, you can fix the cycle of the middle on homology class. So it's a 2n-dimensional real manifold. Calabi-Yau is 2n-dimensional, and fix a half-dimensional cycle, and considers this sort of function. So just integrate the holomorphic volume form, which is unique up to multiplication by constant, and integrate that over the fixed cycle. With the denominator is just a sort of normalization, because this holomorphic volume form is unique up to only up to multiplication by constant. And it's shown that if z in the moduli, this point is on a stationary point with no non-vanishing value, then it gives a minimizer of this function. And it satisfies what's called Moore's attractors equation given by this form. So this represents the Poincare dual of gamma, and that is this, equal to the real part of the holomorphic volume form up to some constant. And okay, so the corresponding Calabi-Yau manifold corresponding to that moduli point Z is called an attractor or attractive Calabi-Yau manifold. The name suggests you're tempted to study this Calabi-Yau. So the typical example of such Calabi-Yau so in the abelian case, the attractors abelian attractors are just a CM type. So the attractor or attractive Calabi-Yau manifolds are sort of a generalization of this abelian variety of CM type. So by studying a moduli space, you get some information about the Calabi-Yau manifold. But this is not the aspect or the structure I wanted to focus on today. And today I wanted to focus on the metric. So just like the moduli of Riemann surfaces, the moduli of Calabi-Yau manifold carries a nice metric called the Veilleux-Peters metric. It's a Kähler metric given by following as follows. So the B model Veilleux-Peterson potential, I use B because in mirror symmetry community, we use B for complex geometry and A for symplectic or Kähler geometry. And I'm going to use A later. So anyway, so the B model Veilleux-Peterson geometry, this is just a classical one. The Veilleux-Peterson, it's a Kähler manifold, so it should comes from a Kähler potential. So Veilleux-Peterson potential is a potential that gives a metric. So anyway, the potential is for local holomorphic family of holomorphic volume form. It's given by this expression. And I think the existence of the Veilleux-Peterson metric is classically known, but it's Professor Tian, I think, who first write down this explicit potential. It's quite useful in practice. But today I wanted to rewrite this potential as follows. So if there exists a basis consisting of formal sum of Lagrangians, and consider sort of with a pairing in a Fukaya category, or this is just an intersection of signed intersection of Lagrangians, and you take the inverse matrix of that intersection matrix, and you can rewrite the potential as this. Okay, so it's not a guarantee that you can always take a Lagrangian representative of a basis here, but in good situation, you can rewrite the potential as follows. And I'm going to use this as sort of guiding principle later, so I label this by 1. So for example, if you consider a family of elliptic curves, so that the fiber over upper half space, where the fiber over tau is just the standard elliptic curve, then by definition, you can compute the potential as follows, and it gives rise to the Poincare metric on the upper half space. And for example, if you consider suitably polarized or lattice polarized K3 surface, the moduli is your symmetric domain of type 4, and the Veilleux-Peterson metric defined in this way is nothing but the classical Bergman metric. So it's a sort of generalization of the classical nice metric.
So by Lagrangian basis, you mean this Ri Lagrangian submanifold?
That's correct. Yeah, but it can be.
Clear this
it's
category, this intersection is invulnerable?
Sorry, intersections.
This chi.
Yeah.
This matrix is invulnerable. Is that clear?
That's right.
Is that easy to see?
Easy. Oh, this is just on alternating sum of layer homology of these.
Invertibility.
Sorry?
Invertibility.
Oh, invertibility. Invertibility on, let's see.
We can assume it.
Sure. From the mirror symmetry point of view, it's a trivial, but I can directly see the invertibility? Yeah, that's a good question. Let me, yeah, maybe not this time, but yeah, sure. It should follow, yeah. Okay, so so far I talked about the moduli, smooth part of the moduli space, and I think the more interesting and more exotic around the boundary of the complex moduli space. And for example, there are many topics to talk about, geometric transitions, and also mirror symmetry is about the boundary of the moduli space too, and many things to talk about. But now let's turn to the Kähler moduli space and see what structure we see. Okay, so the moduli of the Kähler structure, which I call Kähler moduli, for example. The Kähler moduli space is much harder to study, and it's related to GIT and symplectic quotient. So for example, if your symplectic manifold is realized as symplectic quotient, you can vary the symplectic structure by changing the level set of the moment mapping. But it's not true that you can always have such a description, or it may not be intrinsic. Here on our guiding principle is again mirror symmetry. Mirror symmetry tells us, mirror symmetry does not really distinguish birational Calabi-Yau manifolds. Moreover, it tells us that the complexified Kähler cone or Kähler cone of birational Calabi-Yau manifolds give local chart of the Kähler moduli spaces. And moreover, we sometimes need to consider a derived equivalent Calabi-Yau manifold as well. So X and Y may not be directly geometrically related. So the picture is like this. Birational Calabi-Yau, which are related by flops, Kähler cone can be adjacent, but on derived equivalent, we don't know the relation between these. There may not be non-geometric phase. And there is an example giving such a picture called Paffian-Grassmann Calabi-Yau manifolds. And physicists Horin and Tong used the gauge linear sigma model to show that they are really connected in a physical phase space. But mathematically, we don't know how we can glue these local charts. So that's sort of motivation. So this indicates that we need to consider sort of category to really define a Kähler structure, moduli of a Kähler structure. So let me introduce the space of stability condition. This seems a little bit scary, but it's not that much. So a stability condition on a triangulated category D consists of a pair. It's a group homomorphism from Grothendieck group of a category to complex number. It's called central charge. And sort of collection of full additive subcategories parameterized by real number on phi here of D. And they're called semi-stable objects. And that satisfies certain axioms. The first axiom says that any semi-stable object which is non-zero, then the value of this Z lies in the phase phi line. And the second is the sort of compatibility of this collection of subcategories and a triangle structure on the category. The last one is Harder-Narasimha filtration. That basically says that any object in a triangular category is an iterated extension of these semi-stable objects. Some sort of compatibility condition. That's not that important. And we consider the set of such stability condition on a fixed triangulated category, and we denoted stab D. And it turned out it's basically Bridgeon theorem. It is naturally a complex manifold, which is locally modeled on this vector space via the forgetful map. So it's a pair, and by forgetting the second part, you get a map. And by this forgetful map, you see that it's really a complex manifold. Okay. So it's just a recipe to construct a complex manifold out of a category. And claim or conjecture is that for Calabi-Yau manifold X, there exists an embedding of the Kähler moduli space into the double quotient. So stab is a set of stability condition, and there is a natural action of autoequivalence of the category. And also you can rotate the on central charge and these semi-stable objects, just to reparameterize on these things. So you can take on this quotient, and the conjecture there exists an embedding of on Kähler moduli, where the triangular category we consider is the derived category of coherent sheaf of X. So basically there are two steps. Given a Calabi-Yau manifold X, you consider a category of sort of vector bundles over X, and using that recipe, you construct a complex manifold. And that complex manifold gives a sort of ambient space over Kähler moduli space. So instead of working on this, we can work on a better space, better ambient space. So stab is sort of an extended version of the Kähler moduli space. It's similar to the small and big, relation between small and big quantum cohomology. So we can study this space as a sort of a substitute of the Kähler moduli space. Okay, so for example, and in the beginning I explained attractor geometry on the moduli space of a complex structure. And you can write down the mirror analog or Kähler analog of that attractor geometry. And the attractor equation considered in this bigger space, ambient space instead of this, is given by this, for example. Of course, still there is still a gap between this space we want and the ambient space, but this has a nice sort of global coordinate and easier to work on. Okay, so let's turn to the metric perspective. So the Weyl-Petersen metric we studied on the complex moduli can be translated to the Kähler moduli. So recall, well, maybe you forget already, but using the we rewrite the Weyl-Petersen potential given by Professor Tian to some Lagrangian language, and you can sort of replace everything in the equation 1 by mirror object. So that's a sort of motivation, a guiding principle of our definition. And this is well defined, of course. And so given a stability condition, you consider sort of a function of this sort. And where, instead of Lagrangians, we consider some basis of K group of the category, and consider Euler pairing of the category and take inverse matrix of that one. And so if X is a compact on Calabi-Yau, this is symmetric, and it has an inverse. So this is well defined. Okay. So that's an analog of the pairing on the Gaia category. So and we call it the A model Weyl-Petersen potential. And it is I cheat a little bit, but it is defined on a suitable subset of the stability condition. For example, we wanted this part to be positive because I wanted to take the log of that one. So there are some conditions like Riemann's bilinear relation, and there's some condition to cut out some suitable subspace. But what you can check is that the Hessian, the complex Hessian of this function is well defined on the double quotient of this sort. Okay, so it's not clear that this is independent choice of it's invariant under autoequivalence and things. Okay, so but the problem is this is well defined, but it's not necessarily give a metric. It's often degenerate. The thing is because I define a sort of a metric on the bigger space, not this space we want to really study. So the metric is I mean, there's no guarantee that there's a nice metric. It's often degenerate. So
dimension of this space could be also bigger.
Sorry?
So I guess dimension of this space could
Sure,
be
yes.
bigger.
Typically, it's bigger, yes. But this degenerate property, at first sight, it's disappointing, but it turned out to be useful later. Okay, so I wanted, sorry. So I wanted to give the simplest example, of course. And the simplest example is an elliptic curve, which is well studied. And if you compute the stability space of the elliptic curve, then this double quotient can be identified as a nice space. And central charge is given by this form. It's a sort of well-known one. And the grothendieck group of the category has a nice basis given by structure sheaf and skyscraper sheaf. And following the definition, you can compute the potential to get this one. So the metric we get in the end is a nice Poincare metric. So it's sort of a nice indication that we are in a good direction. Oh, sorry. And here's non-trivial example. Let A be on self-product of the elliptic curve. Then there is an identification of the double quotient of the stability space on this Ziegler modular variety. And moreover, the V-beta symmetric we define on this space is identified with the classical Bergman metric on the right-hand side. So the point of the theorem is well, there are two parts. First, we need to identify this space with this one. This is basically on Bridgen's work. We closely follow his work. And the main point is just identification of this metric. So in that case, this embedding is really isomorphism and nice. And there are a few remarks to make. So first, we consider self-product of elliptic, which seems sort of trivial thing, but it turns out to be not. The complex structure of this is one-dimensional, and the same as the elliptic curve, but the Kähler structure is different. It's three-dimensional, so it's non-trivial. And this is compatible with the mirror symmetric observation too, which I skip. And what about quintic threefold? The existence of stability condition for quintic it's not been proven, but conjecturally it's given by this central charge, where this Q is sorry, maybe I should explain it. We consider complexified Kähler parameter tau h, where tau h is a polarization, tau is an element in the upper half space. And Q is an exponential of that, and N is an Gromov-Witten invariant of X. Then the central charge is given by this. And if you compute the potential, you get this, asymptotically, it's given in this form. And this is nothing but the sort of deformation of the Poincare metric on the upper half space, especially when Q is sufficiently small, it's non-degenerate. And actually, the sort of metric aspect of Kähler moduli space has been studied by Pelham-Wilson before Bridgeland introduced the space of stability conditions. So he doesn't know about the Bridgeland. I mean, there's no way, but this sort of direction, research direction was initiated by Pelham-Wilson. Okay, so lastly, I want to mention conjecture, refining Bridgeland's original conjecture. So there exists an embedding of the Kähler moduli space into this a little bit smaller space. And often our metric is degenerate. It doesn't really give you a metric. But you can pull back the potential to the moduli space, and it's non-degenerate. It's conjecture that gives the Kähler metric. Moreover, this is compatible with mirror symmetry in the sense that under mirror symmetry, the metric here and classical V-Peter symmetry can be identified. So we don't know the definition of this Kähler moduli space, but you can make use of the degeneracy condition of our metric to sort of get information about this embedding. This is sort of one application of our work. And that's the end. Thank you very much.